Good afternoon. Today we will discuss about the magnetic field due to the currents. Some subchapter that we will discuss is about what is the physics of the magnetic fields due to the currents, and then the second is how to calculate the magnetic field due to the currents, and then force between the two parallel currents, Ampere's law, solenoid and toroid, and also a current carrying coil as a magnetic dipole. Okay, in physics, how we can explain the phenomenon that there is a magnetic field in around a current if we have the wire like a cable or something else, the material or something that contain a current. So around the that material, around the cable or around the wire, we have a magnetic field because the moving charge particle, if the moving charge particle, we know that there is a two charge particle. The first one is electrons, yeah, and the second is hole, right? Yeah, we have talked maybe in the beginning of this class we talk about these two kind of charge particle. And if the moving charge particle, electron or hole, move from one place to another place, it will be produce a magnetic field around itself. So it will be generates a magnetic field around the currents. So if we have a wiring like the yellow one is the cable containing a current, and a length of vector ds has a length of ds, and whose direction is the direction of the current in ds. So if we want to measure the magnetic fields in P, like this one is in here, we want to calculate the magnetic field in P. So how to calculate? We have to split the cable into small pieces. Yeah, like we can see that this is the red the red one, the dot of the small pieces of the cable ds. So from the ds we can calculate the magnetic fields in P. So the first we have to pick the Biot-Savart law. Biot-Savart law say that the dB, or the small magnetic field d, this is like the partial magnetic field, is equal to mu 0 IDS cross R per 4p R square. So this is the Biot-Savart law. And then the permeability constant whose value is defined, so mu 0 is 4v cross 10 minus 7 Tesla dot ampere, or 1.26 cross 10 point minus 6 Tesla meter per ampere. So this is the permeability constant. So this is Biot-Savart law. So the magnetic fields in P is this one. So if we know the mu 0, like this one, this is the constanta, and we know the currents, and we know the ds here, the ds, and also r, this is the distance between P and the ds, we can calculate the small pieces, or the fractional fractional of the magnetic field in P, like this one. And then if the magnetic, this is the magnetic field due to a current in a long straight wire. So if we have a very long straight wire like this one, so how to calculate the total magnetic field in P? So we can see that here the P and the yellow one is the cable, and we divide the long straight wire with a small pieces wire like DS. This is the small pieces wire to calculate the magnetic field. So by using the DS and then we make integral of the DS, we can get the total of magnetic field. We can see later. So the distance between the DS to P is small r, and also the distance between the P to the long wire is big R here. And then the distance between DS to this one to this point is S here, and the current is the I. So we look the this one, this Biot-Sarfat law, the first we talked before. dB is equal to we can see that ds cross r. We can this one, yeah, we can replace it with the sin theta. Okay, yeah, ds cross r, yeah, ds cross r, this one, this is ds, this is r, yeah, this is ds, and this is r, this is the theta. So the ds cross r is equal to sin theta ds, and then the remaining equation is similar. So this is the dB. So to get the total magnetic field in P, so we have to make integration of these equations. So we have to make integrations. So B is equal to because we can see that this is from one side and another in another side like this one. So we have to make two, yeah, like a pair. So this is the first one and another here. So we have to multiply by 2. B is equal to integral from 0 to unlimited dB. Okay, so it's like from here to here, and then from here to here. So it means that this is to multiply by 2 in the integration of the dB. So we make integration of this equation, so we can get these equations. Mu 0 I per 2v integral 0 to unlimited sin theta ds per r square. And then we've seen that the small r here, this is the small r here, is s quadrats plus big R quadrat here. This is the small s quadrat, and this is the r big R quadrat. So we can get these equations. And then sin theta, this is the theta. Sin theta is equal to sin phi minus theta. Yeah, it's like a mathematics in senior high school. Yeah, we know that this one. So it's equal to r per square of s quadrat plus r quadrat. So we can use these equations to replace the sin theta here. So we can get that the b is equal to mu 0 I per 2 phi integral 0 to unlimited big R ds per s quadrat plus r quadrat 3 per 2. So the first one, this is constanta, so this is the step is remains constant. So the another part, so we make integration of this part, so become this part. So the total after we calculate, we can get that the magnetic fields due to the current in a long straight wire is mu 0 I per 2 V R. So it's only mainly affected by the currents. This is the current I, and then the R. R is the distance between the wire and the P. I mean that's this one. This is the distance, the smallest distance between the cable to the P. So it's only affected by two parameter, both parameter. Okay, so this is for the long straight wire. And then if we have infinite straight wire, so it's like we didn't have to multiply by 2, so it's only from this one to this one, so it is only one side, so we don't have to multiply by 2. So for the semi-infinite straight wire, the B is equal to mu 0 I per 4 V R. And then the magnetic field line produced by a current in a long straight wire, so we can get that this is the current. The currents in and the direction is cross, it means that's the in current into the page, so you can use the right hand rules. So your thumb is the direction of your thumb is the direction of the current. It's like direct into the page, and then the direction of your forefinger is the direction of the B. You can practice for this. For this, we can see that your thumb going to the page, and then forefinger is the direction of the magnetic fields. Okay, so this is the direction of magnetic fields due to the current. So it's like this one. This is the right hand rules. Okay, and then how to calculate the magnetic field due to current in a circular arc of wire. So it's a circular arc like this one. So this is the wiring contain a current I, and then from C, the center of the circular arc of the wire, uh, the radius is R, big R, and then the angle is this one, theta. So we can use using the Biot-Savart law, dB is equal to mu 0 IDS sin theta per 4 VR square. So we use the sin 90 degrees, so we can get this equation, mu 0 IDS per 4 VR square. And then to get the B, we make integration of this equation, so we can get this equation, mu 0 I per 4 V R integral 0 to theta d theta. So we can get that the B is equal to mu 0 I theta per 4 V R. So this is the center, at the center of circular arc. So here the magnetic field magnitude is this one. Okay, so and another topic is a current carrying coil as a magnetic dipole. So for a loop, theta is equal to 2V. It's like this one. So this is a loop at the center of the loop. So So we can see from before that in the center of the circular, so the B is equal to mu 0 I theta per 4 phi r. Okay, or yeah, or in another or in another before we make integration. So this is the previous the first equation. So we write again here. So this is the final, and then this is the beginning equation to define the magnetic field in the center of circular arc. dB is equal to mu 0 id as in 90 degree per 4 vr square. So if we have uh, P like this one, P with the distance of Z here from this cable, yeah, this cable is like we see from another angle. So this is like make circular, but it's like yeah, it's like not a circular horizontal, but this is the circular, this is the circular, it's like this one. So we see from in front of the wire, and then the current direction is actually is different. Here this is like go to the paper, and then this is out the paper. So how to calculate the magnetic fields in P? So we can see that to calculate the magnetic fields in P, so we have to yeah, to check all the point in the wiring, and or in another way we can see that um, the dB here, the small fraction of magnetic field due to a magnetic dipole like this one, we can make illustration like in this figure. So the direction of dB is like this one. So this make a 90-degree angle with this one, with the R. So this is 90-degree angle here. So this direction of the dB, we can make a differentiation between the x-axis and y-axis. This is the x-axis and this is the y-axis. We can see that if we make a projection of all the dipole to this one here, like this one, here like this one, all the wire make a circular, so we can imagine that the x-axis will cancel each other. So this one, the total of the dB in x-axis is equal to 0. Okay, is equal to 0. So the remaining component is only the dB in y-axis. So to calculate the total magnetic fields because of the magnetic dipole, we only have to calculate the integration of the dB in y-axis like this one. And the dB in y-axis is we can see from this equation that mu 0 I cosinus alpha, because this is the angle between the dB to dB y-axis is alpha, so since 90 degree we can replace it with the cos alpha ds per 4 vr quadrat. Okay, So the small r here is, this is the small r is equal to big R quadrat plus square of big R quadrat plus z quadrat, and cosinus alpha here, alpha, this is the alpha, yeah. So this is the big R per small r, so we can get this one. So we can replace the cos alpha using this equation, so we can get that the integral of dB in y-axis become this one. So we can get that the bz or b in y-axis on the total magnetic field due to the magnetic dipole is mu 0 dot I r big R quadrat plus per 2 R quadrat plus z quadrat 3 per 2, or we can replace I r square per v with the mu, so we can replace this one, so this equation become this one, mu 0 per 2 v mu per r quadrat plus z quadrat 3 per 2. Okay, okay, so this is if z is um, more larger than big R, so bz become this one, mu 0 per 2 v mu per z triple. So if we have a two current carrying wires exert magnetic force on one another, so if we have a two wire like this one, wire 1 and wire 2, and if they have a anti-parallel current like this one, this is anti-parallel, so the currents repel each other. If we have a parallel current like this one, E1 and I2, so we can get that it will be attract each other. So this is the Ampere's law. So we can make a total current by check the total magnetic fields around the currents, or closed integral of B ds is equal to mu 0 E and close. So the loop on the integral sign means that is to be integrated around a closed loop, or called an Amperian loop. The current E enclosed is the net current encircled by that closed loop. Okay. Okay. So what is the magnetic field inside a long straight wire with uniform distributed current? So if we have the material like this one, so this is the currents I here, this is the wire surfaces, and this is the Amperian loop. So to calculate the magnetic field in this wire surface, so we use this equation before, like we can see this one in Ampere's law. So closed integral B ds is equal to B closed integral ds is equal to B 2 V R, and in E enclosed is I V small r quadrat per V R big R quadrat, because of this one. This is the current here. The current is in yellow, orange ones. Uh, so we make a comparisons. This is this one, and then the V R, big R is the total surface. So we can calculate the I enclosed. So the B to VR, so the total B in this surface is become mu 0 I. So we can see that this one is this one, yeah. So we can see that from the Ampere's law that closed integral BdS is equal to mu 0 En closed. So B2VR is equal to mu 0 En closed. So we can see that this is the mu 0 and this is the En closed. So this is the En closed. So we just make multiplication, so we can get that like this one. Yeah, and also this we have to also calculate this 2VR here, so we can get that the B in this material become this one. B is equal to mu 0 I per 2V big R quadrat dot small r. And then this is the loop of the current. For a single loop, the magnetic field at the center is B is equal to mu 0 I per 2R. And if we have n turn, so we have to add the n here. So B become of n, B become n mu 0 I per 2 big R. So this is if we have the turns, so it's like a solenoid or something else. So if we make a comparison of wire with the bar magnet, so this is the loop wire and then this is the bar magnet. So we can see that for the loop wire, so the magnetic field, the direction is become like this ones, and the bar magnet also like this ones, and this is if we make the current around the magnet, and this is if we make a current around the magnet. So this is the magnetic field of solenoid. So we make a turn of the circular wiring like this one. So we can see that we can calculate the B by using the Ampere's law. Closed integral B ds is equal to mu 0 En closed, and En closed is equal to In dot h. N is the number of turns, and h is this one, length of the solenoid. So we can see that the BH is equal to mu 0 ENH. So the B is equal to mu 0 IN. So this is the ideal solenoid. So the total magnetic field in solenoid is only determined by the current and also the number of turns. It's not related to the length of the solenoid. So this is the for toroid. It's like solenoid, but they make a circular like this ones. So we can use this one. B dot 2VR is equal to mu 0 In. So the B is equal to mu 0 In per 2V dot 1 per R. Okay, so this is the all of this chapter, and this is the exercise, and I will discuss in another video. Thank you. Good afternoon.